The interstellar comet known as 3I/Atlas, also cataloged as C/2025 N1 Atlas, and A11PL3Z, represents one of the most extraordinary astronomical discoveries of recent years, and its journey through our solar system has offered scientists an unprecedented chance to observe an object that originated far beyond the gravitational reach of our Sun. First detected on July 1, 2025, by the NASA-funded Atlas telescope located in Rio Hurtado, Chile. This comet immediately captured attention due to the unusual characteristics of its orbit and brightness. Arriving from the direction of the constellation Sagittarius, its inbound trajectory alone raised the possibility that it did not originate within the family of icy bodies normally associated with the outer regions of the solar system. Subsequent analysis confirmed that its path through space was hyperbolic, meaning it was not gravitationally bound to the Sun, and therefore the comet was making a one-time passage before returning to interstellar space. Its eccentricity and extraordinary hyperbolic excess velocity suggested a distant origin, possibly from another stellar system, making it only the third known interstellar object detected after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. What made 3I/Atlas particularly remarkable was not only its hyperbolic nature, but the extremity of its orbital parameters. Its eccentricity was far higher than that of either of the previous interstellar visitors, and its excess velocity, meaning the speed it would retain after escaping the Sun's gravitational influence, was among the highest ever recorded for a natural object entering the solar system. These qualities immediately classified it as the most dynamically extreme interstellar object yet identified. Astronomers across the world recognized the importance of observing it as closely and as continuously as possible, especially as it approached perihelion, its point of closest passage to the Sun. On October 30, 2025, 3I/Atlas reached this pivotal moment in its journey, passing within 1, for astronomical units of the Sun, a distance of roughly 210 million kilometers, slightly within the orbit of Mars. At perihelion, the combination of solar heating, gravitational acceleration, and volatile sublimation caused the comet to brighten and release gas and dust into space, forming a complex coma and tail structure. During this phase, the comet achieved its maximum velocity, traveling at an astonishing 68 kilometers per second. However, because it passed relatively close to the Sun from Earth's point of view, the comet became temporarily unobservable to ground-based astronomers. The bright glare of the Sun overwhelmed the faint light reflected by the comet, hiding it from even the most powerful terrestrial telescopes. Despite this temporary observational eclipse, astronomers eagerly awaited the post-perihelion phase when the comet would re-emerge from solar proximity and could be imaged again. True to expectation, shortly after perihelion, 3I/Atlas began to move into a more favorable position, gradually separating from the Sun in the sky, and by the end of October, the first optical images following its solar passage were captured. The earliest post-perihelion image was taken on October 31st by astronomer Qiqing Zhang at Lowell Observatory using the Discovery Telescope. This image provided crucial early clues about how the comet had reacted to the intense heating and gravitational stresses near the Sun, and whether its nucleus remained intact or had fragmented significantly as some comets do during such close encounters. Soon after Zhang's initial observation, additional astronomers joined in documenting the comet's evolving structure. On November 8th, a team from the ICQ Comet Observations Group succeeded in imaging 3I/Atlas when it had reached 29 degrees of separation from the Sun. Their images revealed an unexpectedly complex system of jets, at least 7 distinct outflows, emanating from the comet's nucleus. Several of these jets took the unusual shape of anti-tails, a visual phenomenon that occurs when the geometry between the comet, Earth, and the Sun aligns in such a way that dust particles appear to project forward rather than trailing behind. These jet structures painted a vivid portrait of a highly active comet undergoing intense mass loss. Harvard astrophysicist Avi Loeb remarked that the presence of so many jets emerging in multiple directions would require a substantial degree of non-gravitational acceleration, suggesting that far more than the typical 10 to 20% of a comet's mass had been expelled near perihelion. Because only a fraction of the expelled debris contributes to directional acceleration, the implication was that the surrounding cloud of dust, ice, and gas represented a remarkably large proportion of the comet's original mass, making 3I/Atlas unusually active compared to standard long-period comets. These conclusions became even more intriguing when, on November 9th, a pair of astronomers from the British Astronomical Association obtained additional composite images using 2 different telescopes. Their observations showed a long, smoke-like tail and at least 2 well-defined anti-tail jets. The clarity and length of these structures provided further evidence of vigorous outgassing and fragmentation processes occurring as the comet receded from the Sun. Professor Loeb emphasized the scientific importance of this complex jet system, noting that it would be an exceptional target for space-based observatories such as the Hubble Space Telescope and the James Webb Space Telescope. As the comet approaches its closest distance to Earth on December 19, 2025, when it will pass at a distance of approximately 269 million kilometers, astronomers anticipate an unparalleled opportunity to study the fine-scale structure of the jets, measure the composition of a coma, and determine more precisely how interstellar comets differ from those native to our solar system. Although the comet will still be far beyond the Moon's orbit, about 100 times larger than the extent of the jet complex seen in the recent images, the clarity provided by space telescopes operating beyond Earth's atmosphere could yield unprecedented detail. Beyond Earth-based and large ground observatories, several spacecraft within the solar system also turned their instruments toward the interstellar visitor. NASA's Stereo-A spacecraft captured a sequence of images between September 11th and 25th, 2025, using its heliocentric imager, 1 instrument. By processing these images into colorized stacks, scientists were able to visualize the comet's rapid motion through the inner solar system at speeds reaching 209,000 kilometers per hour, providing context for how intensely solar radiation and plasma interact with an object moving at such extreme velocities. Unlike most comets that evolve relatively slowly as they approach and recede from the Sun, 3I/Atlas showed rapid morphological changes, likely due to both its speed and unfamiliar composition, shaped by environments far different from the Kuiper Belt or Oort cloud where most comets originate. Other spacecraft contributed additional observations across various wavelengths. NASA's MAVEN spacecraft captured ultraviolet images of the comet's coma on October 9th, revealing concentrations of hydrogen atoms that highlighted the sublimation of volatiles such as water ice. The ultraviolet view provided by MAVEN's IUVS camera allowed scientists to detect how solar radiation was stripping material from the comet, offering clues about its chemical makeup and how its structure responded to the Sun's intense heat. Meanwhile, the HiRISE camera aboard NASA's Mars Reconnaissance Orbiter produced detailed close-ups of the comet on October 2nd. From its vantage point orbiting Mars, HiRISE was able to capture surface and coma details that are difficult to observe from Earth, creating a rare multi-platform observational campaign involving both ground-based and deep space assets. All these perspectives, from Earth, orbiting telescopes, and interplanetary spacecraft, combined to form the most comprehensive study ever conducted of an interstellar comet. As 3I/Atlas continues to drift outward and fade from view through December and early 2026, astronomers will continue to analyze the wealth of data collected, comparing its behavior, composition, and activity patterns to those of other comets. Each new observation adds to the understanding of how objects form in distant planetary systems, and how conditions in those systems differ from our own. Interstellar objects like 3I/Atlas serve as messengers, carrying with them the physical signatures of environments many light years away. By studying them, scientists gain clues to broader questions: how planets form around other stars, what materials those systems are composed of, and how their icy bodies evolve over millions of years. In the case of 3I/Atlas, the unusual jet activity Extreme orbital characteristics and vigorous mass loss suggest that its internal structure and chemical composition may be distinct from the typical comets shaped by our Sun's long-term influence. Whether it carries signatures of organic molecules, noble gases, or minerals not commonly found in solar system comets, remains a subject of ongoing investigation. Regardless of the final conclusions, the comet's visit represents a rare and fleeting gift, an opportunity humanity may not see again for years or decades. As it fades back into the cold darkness between the stars, 3I/Atlas leaves astronomers with an extraordinary trove of data and a renewed sense of wonder about the dynamic, interconnected galaxy of which our solar system is just one small part.